Good morning.
Good morning, Professor.
Good morning.
Okay, so we're in test 4 and we are going to look at heating curves today. And then if we have time, we'll do a bit of review as well. Okay, so heating curves. This is the heating curve for water. And what we have here is temperature on the y-axis and heat absorbed on the x-axis. Now, as you know, what water does is it starts out as a solid at low temperature. The temperature is below 0 degrees. And then it will turn into a liquid. And then that liquid will in turn turn into a gas. So this energy diagram is reflective of the changes that occur as the water absorbs heat. Now, this particular heat diagram for water, I've got 18.02 grams of it. The reason I chose 18.02 grams of water is because that is the molecular weight. And you'll see the relevance of that in a little bit.
Professor, you're not screen sharing. You can't see a diagram.
Oh, well, that's nice to know. Sorry about that, folks. That would be super helpful. Sorry about that, guys. I don't often make that mistake, but yes, I made it just now. I'm guessing that's, yes, you're not screen sharing. Thank you so much for letting me know. All right, here's the diagram I'm talking about. So we're starting out here at -5 degrees, which is below 0, which means it's in the solid state at this point. And then it will turn into a liquid, and between 0 and 100, it's in a liquid state. And between 100 and 110, it's in the gas state. Does anybody have any questions so far? So this is just water, right? That's what we're talking about. Now there's two things at play here. The first thing is that when water is in a certain state, let's say liquid, for example, between 0 and 100 degrees, then we can use this equation. Let me get rid of this here. We can use this equation, Q equals mc delta T. This is an equation we've used before that involves heat capacity. And this is used for specifically for anything that's in a constant state, for example, liquid water here. And the way that I would calculate the heat absorbed during that temperature increase between 0 and 100 degrees is to do 18.02 grams, because that's how much water I have here, times the C. Now, the C I want is the C for water liquid. As you can see, the heat capacity for ice, water liquid, and steam are all different. I want to use the water liquid one, which is 4.180 joules per gram per degree Celsius. And then we've also got the delta T. Now, the change in temperature during the time that water is liquid is 0 to 100. So it would be times 100. We'll go 100.0 degrees Celsius. And this will give us the heat used during that time. Let me go ahead and do that calculation here. I don't know if I've done it on the screen here. I don't think I have. So 18.02 times 4.18 times 100. So that would be 7532 joules. So what that represents is the heat absorbed while the liquid is in the water state. So that's that value right there. You'll also notice there's plateaus here. Now, by plateau, I mean it's an area where the temperature is not changing, but heat is being absorbed. So what's happening during these plateau areas? Well, what's happening is that the water is changing phase during those plateau areas. Now, what I mean by that is initially at 0 degrees Celsius, water is a solid. And then as it absorbs heat, it turns into a liquid. But here's the most important point. As it is turning into a liquid, the temperature of the water is not going up. I'll say it again. As the solid water is turning into a liquid, its temperature is not going up. All the energy is going into the phase change. All right, now I'm going to do a poll here and I'm going to find out how you feel about that statement. How do you feel about that statement? About what's going on with the plateau? 5, 4, 3, 2, 1. All right. Any questions? Any questions? Okay. So let's talk about how we figure out how much energy is absorbed during the phase change. To do that, we use these values here. We've got the delta H of fusion and the delta H of vaporization. Now, the delta H of fusion, I know fusion is kind of a weird word for you. You probably haven't heard it before. But fusion is the phase change from liquid to solid. In my view, it's the same as melting, but fusion, you can look upon it as being fusing to become a solid, if you will. Delta H of vaporization, that is the heat required to make it a vapor, a gas. So that one's pretty easy to understand. That's this plateau right here at 100 degrees. In order to get the heat on the plateau, so this is on the slopey bits, right? So that's slopey bits. Does anybody not understand what I mean by the slopey bits?
Okay. What do you mean by that?
I mean, it's on a slope, not a plateau. Is that okay?
Okay.
Is that okay, Michael?
Yeah.
Okay. So that's on the slopey bits. And now on the flat bits, Q is equal to, in the case of the solid here going to liquid, fusion multiplied by the number of moles. Now if you look at the unit here, the unit is 6.010 kilojoules per mole. So as you can see, by multiplying by the moles, you end up getting kilojoules. And as we already have stated here, I used 18.02 grams of water because that is 1 mole of water. So I'm going to multiply by 1 mole. Now there is a bit of a catch here because if I just leave it at that, I'll end up with kilojoules. But what I'm looking to do here is figure out the sum of all of these. And if I'm going to figure out the sum of all of these, then what I'm going to have to do is convert this into joules so that I can compare apples to apples. So this requires one more step, and that is a conversion into joules. So times 1,000 joules over 1 kilojoule, which would be 6,010 joules. So that would be the energy required for the straight phase change, and that's where that 6,010 comes from. Does anybody have any questions?
So where did you get 6,010? I'm sorry, I'm just trying to...
Do you see I've got the value for delta H of fusion right here?
Okay, yep, sorry.
You'd have to be given that, Joseph.
Thank you.
Okay, all the values will always be given to you with the problem. You'll always get the heat capacities of all the phases of the substance, as well as the delta H of fusion and the delta H of vaporization. Does anybody have any other questions about this? All right, let's see. How do you feel about this so far? How do you feel about this so far? 5, 4, 3, 2, 1, 0. It's good. Everybody understands it. I like that. Let's move on. So this is the kind of question that you are going to get on the test. Except that, you know, I don't think you'll have, I don't think you'll be given any of these values here. So but I do have a problem sheet that is similar to this, but it's still helpful in doing the one on the test as well. So I'll show you the one on the test too. So this is all the data that you're given here. Now this was water, so we already knew what the melting and the boiling point of water was. This is some fictitious, some substance that I'm calling compound X. Now for this one, I need all the heat capacities that I mentioned earlier, but you also get the molar heat of fusion and vaporization that I already talked about as well. But here, in addition to that, you also need a melting point and boiling point. Now remember what the melting point and the boiling point represent. The melting point is the temperature at which something will change from a solid into a liquid. The boiling point is the temperature at which something will change from a liquid into a gas. In other words, these phase changes here, the plateaus, the flat parts, we already know what the temperature those are occurring at is. At the melting point and the boiling point, respectively. All right, I'm going to see how you feel about that. How do you feel about melting point and boiling point with respect to this diagram? Let's see how much you've understood it so far. How do you feel about melting point and boiling point? 5, 4, 3, 2, 1, 0. I don't know why people don't vote. You don't have to vote, but you should. All right. Any questions then about melting point and boiling point? Okay. If nobody says anything, I'm just going to assume that you don't have any questions. I don't know what else to do about that. Okay. The mission here, you've already been given the values of certain places on the actual diagram itself here. 3,400 for the first slopey part and 6,000 joules for the second flat part here. What you're looking for are the values on the first flat part, the second slopey part, and the third slopey part. So let's first of all talk about this one here, this flat part. So the Q value for that is going to be the delta H of, well, that's solid to liquid. You can see there I've got the phases written, solid, liquid, gas. So solid to liquid, that's a delta H of fusion that I'm interested in there, multiplied by the number of moles. Delta H of fusion is 2.000 kilojoules per mole. The number of moles. We'll take a look at the compound here. I'll do that up here separately, the number of moles of X. I have 170.00 grams of X. I need to get the number of moles. So to do that is times 1 mole of X over the molecular weight of X, which has been given to me as 85.00 grams of X. So that's 2.000 moles. All right, I'm going to stop here for a second. Is everybody okay with my mole calculation? How do you feel about the mole calculation? How do you feel about the mole calculation? 5, 4, 3, 2, 1, 0. Okay, so any questions about getting the moles? Okay. So the number of moles, as we said, is 2.000 moles. And I will also, during this step, convert this to joules, times 1,000 joules over 1 kilojoule, which will give me 4,000 joules. Any questions? So that is for space 1. Now let's look at space 2. That's a slopey bit, and that's going to mean Q equals mc delta T. All right, whoops. So a good idea, I think, when you're faced with this problem is draw out the graph again. And then put the temperatures for the melting and boiling points on the side here. Now the melting point, let's see, that's solid, liquid, gas, is, let's see, the melting point it says here is minus 10 degrees Celsius. And the boiling point is 60.00. So 10.00 and 60.00. All right, anybody got any questions so far? Okay, so MC delta T, M is, well, look at that, it says 170.00 grams. That's the mass of compound we're dealing with. The C, we're looking for the C of the liquid, heat capacity liquid, 3.000 joules per gram per degree Celsius. And multiplied by the change in temperature. Now this gets a little bit trickier. The change in temperature is going to be the difference between 60 and minus 10, which is 70.00 degrees, not 50. Anybody have any questions about that? The 70?
Why would it be 70?
Well, I'll give you an example with a number line here. So let's say we have minus 5, minus 4, minus 3, minus 2, minus 1, and 1 and 2. What's the difference between 2 and minus 5, Michael?
Maybe minus 7?
Not minus 7. The difference. It's just 7.
The 7?
Yeah. So that's what's going on here. It's 60 essentially plus the 10 to get to the negative. The same thing happens if you're doing this kind of subtraction or difference, or, you know, along a number line, same kind of deal. Do you understand what I'm talking about?
Yeah, so it'll be just 7 then.
It would just be 7 for this, but this one's 70.
Oh, okay.
You get it? With the 60 plus the 10.
Oh, I get it now.
It's kind of like 60 minus 10.
Yeah, I get it. Thank you.
Okay, good. Anybody else have any questions? See, Michael, I'm glad you asked that, because I know that there were a bunch of people who were scratching their heads wondering about how I got 70. But now they're not, right? I hope. So that would be 35,700 joules once we do the math on that. Okay. All right, how do you feel about number 2? How do you feel about number 2? Five, 4, 3, 2, 1, 0. There's still 2 people not voting. Samaya and Alex, why don't you have your video on? I know I don't usually check, but I'm checking now. Samaya, if you don't turn your video on, I'm going to kick you out of class. Unless you can come up with a good reason for why you don't have it on. Well, do you usually don't have a cam? Is that the story, Samaya? I mean, I made it pretty clear. I made it pretty clear from the outset. You know, I don't think it's excusable. I really don't. All right. So the three people here have an issue with this. Can I get some questions, please? Questions. If you have an issue with it, you need to, it must be because you don't understand where one of these values is coming from. Either the 170, the 3, or the 70. Or all three, I don't know, but until I know that. There's three people who have an issue with this. I need some questions. Okay, so for number 3, that's another slopey part of the graph here. That's going to be MC delta T as well. So again, it's going to be 170.00 grams. That's what's given here in the question. And then 2.500 joules per gram per degree Celsius. That is the heat capacity of the gas, because that is the gas there. And then it's going to be 15.00 degrees for the change in temperature. Now, how do we know that? If you look at the question here, we're looking for the changes in heat from minus 20.0 degrees all the way up to 75.0 degrees Celsius. So the top of the gas here represents the value that we're seeing in the problem. So the difference there, how we're getting to 15, is 75 minus 60. So it's the difference between those two. All right, does anybody have any questions? All right, how do you feel about that, number 3? How do you feel about number 3? 5, 4, 3, 2, 1. Got everybody voting this time, that's good. All right, still 2 people not understanding. Are there any questions?
Can you just explain like where you got everything for part 3?
Okay, so you've got the mass, which is the mass of the compound, 170.00 grams. You're okay with that, Joseph?
Yes. Yeah.
Okay, the C is the heat capacity of the gas, which is given here, 2.500 joules per gram per degree Celsius. Is that okay?
Yes. And
the temperature difference is the difference between the boiling point, which is given, 60.00 degrees, and the top value, which is 75.0. Maybe that's what's confusing you, the 75.0. Yes. Well, it's just given to you in the problem. I mean, we're looking for the temperature change from minus 20.0 all the way up to 75.0.
Oh, okay. I was looking at the melting point and boiling point, wondering where you got that. Okay, thank you.
Okay, so that part of it's from the problem, okay? Now, after you can see that certain of these values were already given here, but when they're all added together, we come up with 59,175 joules, which is the sum of all of those different values. All right, does anybody have any questions? Let's take a look at what this problem looks like. On the test. And there it is there. This is question 33 on the test. And for this one, you'll need to come up with all the different values here, A, B, C, D, and E. You are given, this is the question here, calculate the total energy required to bring 260.00 grams of compound X. You're given the molecular weight here, And you're also given the temperatures as well, minus 65 to 210.00, minus 65.00 to 210.00. You're also given the melting points and the boiling points as well. So I think a good place to start with this problem is to redraw the diagram . Solid, liquid, gas. And, you know, we've got A, B, C, D, and E. And the bottom temperature is where we're starting, which in this case is, it says it's minus 65. It says it's minus 65 and we're going up to 210. So the bottom value here is minus 65. The melting point is the first flat bit, and that's 75.00 degrees. The boiling point is the next flat bit, which is 170.00 degrees. And the top value that we're looking for is 210.00 degrees. So I think that's probably a good idea first, is to put those temperatures on there so you have a better feel for what's going on. So we'll do A first. So that's an A there. So A, and that's a slopey bit. So Q equals MC delta T. And the mass is, well, according to the problem here, 260.00 grams. We need the heat capacity of the solid. That's given to us as well. 3.659 joules per gram per degree Celsius. And the delta T is going to be the change in temperature from minus 65 up to 75, which is going to be 140.00 degrees. So we do the math on that. And I get 133,188. Or actually, I'll just take it down to the whole thing, 187.6. You're probably better off not converting it to significant figures, but you could if you wanted to. There should be enough tolerance in the answer to deal with that. But for these kinds of things, you don't really need to convert it down into significant figures. Does anybody have any questions about A? Any questions about A? Okay, so B is the solid part going to the liquid. So that's going to be Q equals delta H fusion times number of moles. Now the delta H of fusion is going to be given down here, 5.118 kilojoules per mole. Now the number of moles is going to equal 260.00 grams times 1 mole of X over the molecular weight of X, which is 80.00 grams. And that would be 3.250 moles. So multiply that by 3.250 and then by 1000 joules per kilojoule. And that'll give us that answer as well. And I get 16633.5. All right, let's see how you feel about A and B. How do you feel about A and B? How do you feel about A and B? 5, 4, 3, 2, 1. Okay, any questions?
I just have one for my A currently. I was doing the practice test on my own, and when I put the formula in, it was giving me close, but like off by a single digit.
Okay,
I just
well,
don't know.
okay, that's something you'd have to email me privately about.
Okay.
And I've put certain specific conditions in there for significant figures as well. So that might be part of it too. Okay, any other questions? All right, so then it's going to be pretty much the same thing for A, B, C, D, and E, and then add all those get added together, and that gives the total, which is what goes in the box down here. So that means that you know that on the test you'll also be given an area down here, another question where you can put your work. You know, this is definitely a good one for you to put your work in, because if you don't put your work in, you get the wrong answer, then you'll get nothing for it if you don't show the values. You might have just gotten one of these wrong, and then that makes the whole thing wrong at the end. So if you put your work in, then I can know that, and I can give you partial credit, more partial credit than you'd get if you didn't put any work in, that's for sure. In fact, you'd probably get no partial credit if you didn't put any work in. All right, any questions? Any questions at all for this one, number 33? Okay. All right, so I will do some quick review here. I don't think I have time for the entire test here. So does anybody have any specific questions that they want me to look at for the test here? Anything that do you have burning concerns about?
Can we do a Vesper?
Oh, well, that means all of them, really. That means all the first problems. It would be 1 through...
Oh, true. Can we just do one?
Oh, no. We'll do all of them. We have to do 1 through 12.
Oh, well, I don't need hybridization or dipole.
Which one do you want? Just be specific, and we'll do that.
Like determining what the shape is.
Okay, all right.
Thank you.
Okay. So we'll start off with this one. And I'm going to do 2 of these problems. I'm going to do number 3 and number 4, okay? Now, number 3 is looking for the overall shape, and number 4 is looking for the sorry, no, number 5 is looking for the shape of the atoms. Okay, so I'm going to do 3 and 5 here. So let's look at SbF2 minus. Now, the first thing we want to do is get the valence electrons for that, which is going to be 5 plus 2 times 7 plus 1, which is 20. So when I do the structure here, I do SbF2 minus. I do F2 here. Now that uses up 16, which means we've got 2 more lone pairs here for a total of 4. So that would be 20. So the Lewis structure looks like this for SbF2 minus. And the overall shape is going to be anything that's bonded to the Sb, an atom, and also the non-bonding electron pairs. So I'm going to put check marks on everything that's included in the overall shape. And that means there's 4 objects. If I'm interested in the overall shape, then what I do is I go up here and I look for the shape that is best described by having 4 objects, and that would be the tetrahedral. So my advice for overall shape is to kind of pretend that the lone pairs are also atoms, and that will give you the overall shape. So the answer there is tetrahedral. Let me see how people feel about that. How do you feel about that problem we just did? 5, 4, 3, 2, 1. All right, any questions then? 2 people partly understand it, so.
Is there a way to know which one, which atoms to use and which ones not for the shape?
Well, if it says overall, you want to use everything.
And then like when you're trying to determine the shape after you draw out the Lewis structure.
Okay, let's say, now the overall for this one is overall, right? That would be tetrahedral. But let's say we were looking for just the shape of the atoms. It's then that you look for specifically the one that has 2 atoms and 2 lone pairs. And that would be this one, angular. And that is the shape of the atoms. So it's really important that you understand the distinction between those two things that we're looking for, shape of atoms or the overall shape. Who asked me this question?
Jack.
Jack. So tell me, Jack, is that okay? The difference there between overall and shape of the atoms?
I think there's still something I'm not getting, but I'm not sure what to ask.
Okay. Well, can anybody else ask a question to help Jack out?
Is X the atoms or the lone pairs?
Well, X is atoms, and the lone pairs look like lone pairs. Okay.
Those balloon-looking things?
Yeah, balloon-looking things. They're the lone pairs, yeah.
Okay, perfect. That's what I was tripping up on.
Okay. Any other questions? Is that help, Jack? I don't know if that helps.
Yeah, that helped a little.
Okay. Now remember that you can't see lone pairs. I mean, if you were to look at this atom under a microscope, you might see the atoms, but you would never see the lone pairs. The lone pairs are invisible. So when you're just looking for the shape of the atoms, yes, the lone pairs are influencing that shape because they're taking up space, but you can't see them. So that's the difference between shape of atoms and overall shape. But overall shape is also important because that determines the shape of the atoms as well, and the hybridization and the dipole. So that's why we need both of those. Okay, let me see how people feel about this so far. The difference between overall shape and shape of atoms. That's what I'm looking for. How do you feel about the difference between the overall shape and the shape of the atoms? 5, 4, 3, 2, 1, 0. Not getting everybody to vote, but anyway, there we go. All right, any other questions? Okay. All right, let me go on to the next one. I'll go on number 5. Yeah, we'll do that one. That seems to be okay. Okay, so GA I3 2 minus. So valence electrons are going to be 3 plus 7 times 3 plus 2, which is 26. So I do the GA and I'll put 3 I's around it. Remember GA, it's GA's in group 3, isn't it? I think it is. Could somebody verify that for me? If you have a periodic table. Actually, I'll look it up here. That's a good idea. It is, yeah. All right, just wanted to make sure I wasn't crazy. Or it's not that crazy. So we go ahead and we put the electrons around the I's, and that's a total of 24. And that means there's 2 left over, and that goes on the GA like that. So the overall shape would be tetrahedral because it has 4 objects. And the shape of the atoms, which is what's being asked for here specifically, let's go back up here. We're looking for something that's got 3 atoms in a lone pair. 3 atoms in a lone pair. And there it is, trigonal pyramidal. So you don't have to memorize anything, you just have to know what you're looking for. So trigonal pyramidal would be the answer.
If GA didn't have a lone pair, would it be just 3 groups?
Yeah, that would have been trigonal planar.
Okay.
If there was no lone pair, the shape of the atoms would have been the same as the overall shape.
Right.
Is that okay?
Yeah, thank you.
Okay. Does anybody have any other questions about this? Okay. Does anybody have any other requests or problems that you want me to look at specifically on the test?
Can you go over number 15?
15, let's have a look at 15. Okay. So the answers to these are in the PowerPoints and in the video that I have for this, for the molecular orbitals. And I strongly recommend that you look into those. Now this one is looking for the 2s anti-bonding orbital. So what the 2s anti-bonding orbital is going to be a combination of will be the 2s and the 2s orbital. You'd have to know what a 2s orbital looks like. Too big. There we go. Now, 2s orbital is going to be spherical, and it's going to be combined with another 2s orbital that's also going to be spherical. Now this one's looking for the anti-bonding, which means they have to be opposite phases. So that'll be plus and that'll be minus. So you're looking for an answer, first of all, that involves these two as 2s orbitals. And then the orbital that it forms is an anti-bonding one because the phases don't match. And it's going to look something like this. And the phases remain the same. So it's plus and that's minus. They don't bond together. So that's what you'd be looking for as the molecular orbital. And we call that a sigma. We call that a sigma orbital, right? And yeah, the one you would be looking for would be this one here. That'd be the answer.
Thank you.
All right. So yeah, I'd recommend that you sort of brush up on that. It's actually not as hard a question as it looks. Not nearly as hard as it looks, really. If you have some idea of what's going on with it, it's not too bad. Does anybody have any questions? Okay. Any other requests for questions here on test 4?
One of the ones
If you
that,
could,
like one of the ones that uses the colligative properties.
Okay. Joseph, I'll get your question second, okay? Jack, do you have one that specifically you want to look at, or all of the colligative property problems? Or it doesn't matter? Jack?
That doesn't matter.
Okay. So let me point out also that there are videos for each and every one of these test problems. So if you're concerned about the actual method of doing these, given the information you have, you can always watch the videos. Were you aware of the video, Jacques? For the test?
Yeah.
Test questions? Okay, good. Okay. So given the following mixture of two compounds, 30.00 mils of X and 685.00 mils of Y. And what we're looking for first then is the molality, because we're looking for delta TF here, which is going to be the molality multiplied by the, delta TF is the molality, or well, actually I should say, let's do it the way I've done it in the past, KF times the molality rather than the other way around. You are given here the KF value, that's a molal freezing constant, 3.885 degrees Celsius per molal. But what we're missing here is the M value here, so we need to find that. So M is going to equal moles of solute, in this case moles of X, divided by kilograms of solvent, which is Y. So if you simplify it like that, it's not so bad. So the moles of X, well, we need the grams of X. We have the mils, so we can do 30.00 mils times the density, which is 1.123 grams per mil. And that would be times 1 mole over the molecular weight, which is 81.00 grams. So that's to get the moles of X. Now that would be 30 times 1.123 divided by 81. And I get 0.4159 moles. That's for the X. Let me know how you feel about that. How do you feel about the moles? Just the moles so far, moles of X. How do you feel about it? 5, 4, 3, 2, 1. Oh, that's really good, isn't it? Look at that. Okay. So we need the kilograms of Y. We do have a volume here. We have 685 mils. So that's what we're looking for here is a kilograms of Y. So it's going to be 685.00 mils times, now this is a little tricky because we have to use the flip of the density here in order to get the mass. Oh, no, we don't. No, we just have to multiply. We just have to multiply by the density to get the mass. And that would be 1.167 grams per mil. So as you can see, the grams will be left at the end, the mils will cancel. That's how I know not to flip it. And then that's times 1 kilogram over 1,000 grams. Yeah, so you only need to flip it if you're looking for volume. In this case, you're not looking for volume, you're looking for mass. And that comes out to be 0.7994 kilograms. So then it's a matter of taking the moles, dividing by the kilograms, and that's going to come out to be I get 1.922 and that'll be the unit, little m at the end there. Moles per kilogram will also work. All right, how do we feel about the molality? How do you feel about the molality? We're not done with the problem yet. 5, 4, 3, 2, 1, 0. Okay. And any questions so far? All right, so we've got the m value now, so we can calculate the, let's see what we've got, 3.885. Degrees Celsius per molal times the molality, which is 0.79, sorry, no, it's not, it's 1.922. And that would be, let's see, I get 7.467. And what this represents is degrees Celsius. And it's a change in temperature. Now, it's freezing point that we're looking at here. We are given the pure freezing point as being 26.00 degrees. So the new freezing point is going to be 26.00 degrees. Remember, we're given that. Minus the value I just came up with, 7.467. Now, the reason it's minus is because it's freezing point depression. Okay, so 18.53 degrees Celsius would be the answer. All right. Does anybody have any questions? So as I pointed out earlier, all of these problems, every last one of them has a video explaining how to do it. So if you get lost while doing the practice test, then you've always got a reference to look at. You've always got those videos to look at. Yeah, I know it's a lot to do, but you know, if you do the practice test over and over, and you don't stop doing it, then there's no reason you can't do well on it. I mean, everybody in this class can get an A on this test if they're willing to do the practice test enough times. No, none of you can sit here and say that I haven't given you enough resources. None of you can say that. You can try, but I'm not going to believe you. All right, any questions? Okay, any other questions about anything else on the test? Joseph, you had one. Joseph.
Oh no, I figured it out.
Oh,
I
you
was
did?
using the wrong formula.
Oh, okay. Any other questions?
Can you go over the bond angles?
Bond angles, okay. The bond angles, most of them can be visualized. There's only one that can't be visualized easily in two dimensions. But if you've got linear, I'll go ahead and write these over here. Michael, would you agree that it's pretty easy to tell what the bond angle is in linear?
Yes.
Okay, that one's easy. Even trigonal is not that bad. That's 120. That's 360 divided by 3. It's a circle. You okay with that one, Michael?
Yes.
Okay. Tetrahedral, that's a tough one because it's three-dimensional, but tetrahedral, you have to just remember this one because there's no way there's not an easy way that I can get you to look at this one. 109.5 degrees. Oops, not C, just 109.5 degrees. You'll just have to accept that. I'm sorry, but that's how it is. It's a solid shape. Now the rest of them are kind of combination. So if you look at the trigonal bipyramidal, you look closely at it, you'll see it's a combination of linear and trigonal. So the linear is the vertical part and the trigonal is the horizontal part where I'm circling right here. So the bond angles on the trigonal are going to be 180, 120, and 90, because 90 is the bond angle between these two x's right here, and the vertical and horizontal ones. And then in the octahedral, it's all 180 and 90. They're all 90 degrees. That's a square there. And those are all 180 and 90. So that's it. The only hard one there is tetrahedral. It's 109.5. Now, why isn't remembering that an issue? Can anybody tell me? Why you wouldn't really have to remember that necessarily? Any thoughts? Well, let's take a look at the bond angle question. The answer to my query here is it's all multiple choice. There's 109.5 there. Surely you can remember that that's the one that's tetrahedral, all the other ones is covered by the other bond angles. So there you go, it's not that bad. Any other questions? Michael, does that clear up everything you need to know about bond angles?
Yeah, thank you.
Okay. Any other questions? Any other questions? All right, any other questions about test? Any other questions related to the test? Well, I want to do a quick poll here. I have to create it though. All right. And I'm looking just for a rounded number here. For many of you, I imagine the number's going to be very round, like 0. It's a very round number, isn't it? All right. Okay. All right, but that's okay. Let's have a look. I'm just interested. It's remember, it is completely anonymous. I'll point that out again here. All right. I'd like everybody to answer this, please. Remember, it's completely anonymous. I have no idea. So I just want to see how many, what you've done so far. 5, 4, come on. You can vote, be honest. I don't know who's doing what. One more. I need one more person to vote. One more. Come on. All right. Okay. Well, it's good to know. It's good to know that all of you, at least people who are here, I don't even want to know the people who aren't here what they've done so far, but at least you guys have done something, so that's good. But you will have to do a lot more. I'm telling you that. I'd say to be successful with this, I think you probably need to do at least 6 hours of just doing that, of doing the practice test again and again and again, at least. I'd say for many of you 9 hours. If you want an A, I don't know. If you don't want an A, then I suppose it doesn't matter as much. But if you're looking for an A, then that's what you're going to have to do. All right, does anybody have any questions? Anything else they want to ask about the test here? Anything else you want to ask about the test? Anything else you want to ask about the test?
Can you go over the hybridization?
Okay. Now the hybridization is going to be based solely on, I've actually already done GAI 32 minus, so I'm going to take advantage of that. The hybridization is based on the we just did this one, I'm not going to do it again. On the overall shape. Now, from what I was telling you earlier, the overall shape here is tetrahedral. Are you okay with that, Michael? Because it's 4 groups. Okay. Tetrahedral equals 4 groups. That means 4 hybrids. And those 4 hybrids are going to be made up of 4 orbitals. So you choose the one that's going to be made up of 4 orbitals, and that would be the sp3, which is made up of 1 s and 3 p's. 1 plus 3 is 4. That's why you'd answer sp3 on that. Is that okay?
Yeah.
All right. So with that, how do you feel? How do you feel about, oops, I don't want to do that. Yeah. How do you feel about hybridization? How do you feel about hybridization? It's a tricky one, especially if you weren't here when I went through it. 5, 4, 3, 2, 1. 0. Come on. 2 more. Yeah. Okay, any questions about hybridization? Okay. All right. I'll go over a net dipole problem here as well. So for something like this one, I already give you the shape and everything, so. So the dipoles run along the bonds from the less electronegative, sorry, from the, whoops. Yeah, from the less electronegative to the most electronegative. Nitrogen's more electronegative than chlorine. And the net dipole then is going to go up and in between the two. And it would be, I guess, northwest, right? That would be the one you'd choose. So it'd be this one here. Okay, any questions about that one?
So if it's northwest because the arrows are pointing and to the left, right?
Yeah, they're pointing to the left, and the arrow, the resultant arrow, or the dipole, runs right in between them, right through the center. Remember remember this dash line means it's going into the page, and the wedge line means it's coming out of the page. So the new dipole or the net dipole is coming straight in between them. All right, I'll ask how many people. All right, how do you feel about that net dipole problem? 1, come on, 5 more left. 2, 5, 4, 3, 2, 1. That's good. I'm really happy with that. That you all, that the most of you understand that. That's good. That could be a tough problem. But you know, that's the thing. If you keep on practicing these, you know, you'll get to see the problems you have trouble with. You can just do those again and again if you want to, until you're completely understanding what's going on with it. It's all a matter of, are you willing to put the time in or not? That's what it comes down to. All right, any other questions? Any other questions about the test? Any other questions about the test? All right, so as you know, there won't be class on Monday, because you'll be doing the test. So use that time wisely. My advice would be try and get the test done, you know, earlier rather than later. Don't leave it till the day it's due. But you know, I get that advice all the time. But most people end up doing it on the day it's due anyway. All right. Any other questions?
I have a question about the lab final.
Okay, well, we can, you can talk to me about that after coding.
Okay.
All right, any other questions? Okay, all right, we'll leave it there for today then. Good luck, and I'll see you all next Wednesday.
Thank you, Professor.
Bye, Professor.
Thank you.
Thank you.
Bye.